Hello. This presentation is on the warning component of ECFAS with the marine hazard side of the project, and more specifically is focusing on the forecast of total water levels at the coast and the identification of thresholds of those water levels that, if exceeded, can trigger coastal flood mapping in the ECFAS prototype. So the objective of this work here is really focusing on the warning component on the marine forcing side with two main objectives. The first one is to provide pan-European validated operational forecast of coastal total water levels. And by total water levels, we mean here the mean sea level that is mostly induced by ocean circulation, plus tides, astronomical tides, storm surges, including wind setup and inverted barometer effect, and the wave contributions, such as wave setup. The second main objective is to provide thresholds of total water level that can trigger the coastal flood mapping. So using the 5-day forecast of total water level and of wave parameter, we can check with identified thresholds if those thresholds are exceeded in the forecast, and if so, activate the rapid mapping of coastal floods of the ECFAS prototype. So now detailing a little bit more those two objectives and how we go towards them. We focus first on the forecast of total water level. And here we are aiming at producing hourly time series of sea level forecast along the European coast, including the contributions from ocean circulation, steric sea level that is induced by changes in ocean density, tides, storm surges, and waves. Those operational forecasts of total water level are based on the Copernicus Marine Service distributed systems over the European seas. Those systems are operational, regional forecast systems. They are based on state-of-the-art model produced by a network of European institutions. They are freely distributed on the Copernicus Marine Service website, and their quality is assessed. So to now from that produce the forecast of total water level at the coast, we are extracting and combining the data from the Copernicus Marine Service ocean physical and wave systems and extracting them at the coastal points that you can see on the right plot here with the different colors showing the different regions of CMEMS. So regarding the ocean models, those are 3D ocean dynamic models. Most of them are including explicitly astronomical tides and storm surges representation. They have a resolution, a horizontal resolution that is ranging from 1.5 to 4.5 kilometers, depending on the region. They provide hourly outputs. They benefit from data assimilation with, for instance, assimilation of observed satellites, sea surface temperature, of sea level anomaly, or profiles of temperature and salinity in the ocean to constrain the models towards observation. And they provide 5 days forecast. For the wave systems, they are based on WARM or WaveWatch 3, state-of-the-art wave models. They have a similar resolution as the ocean models with hourly outputs as well, 5-day forecast. And they are coupled to the surface currents that are provided by the ocean systems. And we're going to be using the wave systems to estimate wave parameters and wave setup. We are also assessing the forecast skills of the models with observations, so by comparing them to observation. And those observations are mostly coming from the Copernicus Marine Service with near real-time and reprocessed observation in situ with tide gauges and wave buoys, as you can see, and you can see that distribution on the left panel. And on the right, you can see also the satellite altimetry along track data that we use with a high resolution of 5 Hertz to assess the models. We show here an example of the assessment of forecast skills. This is an activity that is still ongoing. And we show that here by comparing the model to tide gauge data somewhere in the European Northwest Shelf model, and you can see the location in the upper right panel for a given period that is in March 2021. And you can see with those different plots, the forecasted sea level, wave height, and wave period at different times. So 5 days ahead a given event, high sea level event, that is noted here with the red arrow. And you can see with the dashed red line, the delimitation between the analysis, where we benefit from observation, and the forecast. And we have an idea here of how the model perform compared to observation that were gathered, of course, after the forecast, with a forecast lead time of 5 days, 3 days for the middle column. And when we are in the analysis mode, so after the event occurred, and we are benefiting from observations and data assimilation, and also more accurate atmospheric forcing. And you can see that even 5 days ahead, so in the 5-day forecast, the model is also capturing the variations of the total water level that are seen by the tide gauge, and even more so in the analysis. A more synthetic view is provided here over the Mediterranean, the Western Mediterranean Sea, with annual maxima error for the year 2020 in meters, and the correlation between the model and the tide gauges, so at tide gauge points. And on the right side, you can see a focus on one tide gauge, which is located in Valencia in Spain, and still for that year of 2020. And you can see in blue the tide gauge sea level record, in red the model sea level, total water level, and the residual between the two, so the error, is shown here as the black time series. And if we focus on the early period of that record, so in January 2020, where we had an extreme event with the Gloria storm, you can see that the model, still in red, is doing a good job as capturing the sea level changes that were recorded by the tide gauge in blue. And you can see that the residual is quite small, even for this extreme event. So we do have now the operational production of total water level forecast at the coast, but we do need to know if we need to trigger the system and the coastal flood mapping if the total water level are just too high. And for that, we need to identify thresholds of total water level that will trigger the coastal flood mapping. And to identify those thresholds, we need a long data record of total water level to identify the historical thresholds. So we are producing a handcast of total water level over a longer period. From that handcast, we will perform some extreme value analysis, as you can see on the lower left plot, to identify threshold. But also, as the awareness system in ECFAS is running with CMEMS forecast, we also need to calibrate the thresholds that are identified from the handcast to the forecast system, because the handcast and forecast system are not exactly the same. And we need to apply some bias mapping between the two of them, so that the thresholds identified with the handcast can be applied to the forecasted total water level. So we detail a little bit more those actions here, with first the production of hourly time series of past total water level and wave characteristics over the last decade. So to do that, we are upgrading a pan-European tide, storm surge, and wave handcast model, which is based on the schism model. It's a 2D barotropic mode configuration with a resolution reaching 2 to 3 kilometers in European shallow coastal zones, forced by the ERA 5 atmospheric forcing, and providing one hourly outputs. We are combining this handcast with CMEMS reanalysis to get the total water level at the coast, and including the mean sea level that is induced by ocean circulation. And we are calibrating and validating also the handcasted total water level. From that, we will develop the threshold. So this is an activity that is for the future activities of ECFAS. So we will go from the handcast of total water level and wave setup to an extreme value analysis to identify handcast thresholds, for instance, focusing on the 2-year return period levels. We will perform some quantile mapping correction to adjust the water level from the handcast to those of the forecast, and you can see illustrations of that on the right hand side of this slide. With those identified thresholds, we will check if their accuracy with past flood event case studies. And if they are not matching very well, we will just loop over that chain to adjust the threshold so that we can get the identified thresholds that will be used in ECFAS. And those will serve to be compared with the forecasted total water level. And if they exceed the thresholds, then we will activate the rapid mapping of coastal floods in other parts of the ECFAS project. So I thank you for your attention. And if you want to know more about the project, I invite you to email us at the email address provided on this slide, or you can of course visit our website. Thank you very much.